All right, welcome to the Explainer. Today, we're going to dive deep into the invisible world of gases. It looks like pure chaos in there, but you'll see there are some surprisingly simple rules that bring order to it all. So here's our game plan. We'll start by looking at the chaos inside a gas. Then, we'll introduce a simple model to help us get a handle on it. From there, we'll see how that model creates real-world pressure, check out the famous laws that pop out of it, and finally, bring everything together in one single, perfect equation. Okay, let's get into it.
To get us started, just picture something super simple, like a basketball or even a party balloon. From the outside, it's just a ball, right? A simple object. But what if we could zoom in, way, way in, to the microscopic level? What's really going on in there? Well, it's a completely different universe. You'd see trillions of particles in this frantic random dance. They're all zipping around, bouncing off each other, hitting the walls. It's just nuts. And the kinetic theory of gases? That's our tool for finding the beautiful, simple order hidden inside all of that chaos. So how in the world do you make sense of trillions of particles doing their own thing? Well, scientists do what we often do with a huge problem. They simplify it. They created a model to help us grasp the basics, and we call this the ideal gas. Now, here's the thing. An ideal gas doesn't actually exist in the real world, but it is an absolutely crucial concept. Think of it like a perfect blueprint. By comparing how real gases, like the air we're breathing right now, behave compared to this perfect model, we can really start to understand them. It gives us a clean, simple baseline to work from.
Okay, so to build this model, we have to agree on a few ground rules. First, let's just pretend all the gas particles are identical, tiny little dots. Second, they're moving completely at random. Third, we'll assume they don't attract or push each other away. They just fly right past one another. And when they do hit something, bam! They bounce off perfectly, like super bouncy billiard balls, without losing a single bit of energy. It sounds like we're ignoring a lot of messy details, and we are, but that's the whole point. It lets us get to the core ideas that drive how all gases behave.
So if we've got all of these tiny particles just whizzing around inside a container, how does that create something we can actually feel and measure, something like pressure? Well, every single time one of those trillions of particles smacks into the inner wall of its container, it gives it a teeny tiny push. It's like an endless, microscopic drum roll happening all over the inside surface. And get this, the scale we're talking about is just mind-blowing. That number, 10 to the power of 23. That's how many collisions are happening on a tiny patch of surface, just 1 square centimeter every single second. Each push is almost nothing, but when you have that many happening constantly, they all add up to create the steady, powerful force we know as pressure. It's what keeps your tires inflated and your basketball bouncy.
Okay, this is where it gets really cool. Once you understand that pressure is just a bunch of tiny collisions, you can start to predict what's going to happen when you change things. Like, what if you shrink the container? Or what if you heat it up? This brings us to the famous gas laws.
This table really breaks it down. First up, you have Boyle's law. If you keep the temperature steady but squeeze a gas into a smaller space, those particles are going to hit the walls way more often, right? So the pressure goes up. Then there's Charles's law. If you heat a gas up, its particles get more energy and start moving faster, pushing the walls of their container outward and taking up more space. And finally, Gay-Lussac's law. What happens if you heat a gas in a container that can't expand, like a pressure cooker? Well, those faster particles just hit the walls harder and more often, so the pressure inside skyrockets.
I love this analogy for Boyle's law. Less space means more pressure. It just makes sense. And that same basic logic, that same cause and effect, applies to the other laws too. When you add heat, you're just giving the particles more energy. That extra energy has to go somewhere. It either pushes the container to get bigger, like in Charles's law, or it just builds up as more pressure inside, like in Gay-Lussac's law.
So we have these different laws, and they're great for describing specific situations. But wouldn't it be amazing if we could roll them all up into one single, powerful equation that covers everything?
Well, that's exactly what happened. When you take the relationship from Boyle's law, and you add in the insights from Charles's law, and then you bring in Avogadro's work on how the amount of gas matters, all of those individual pieces just snap together. It's like they were all parts of a bigger puzzle, leading to this one grand, unified formula.
And there it is. PV equals nRT, the perfect gas equation. It is so elegant. It perfectly connects pressure, volume, the amount of gas, and the temperature, all tied together with a single number, the gas constant R. This is it. This is the ultimate payoff from our simple little model of bouncing particles. A truly beautiful piece of physics that links the invisible world to the one we can see and measure.
And that's really the big takeaway here. The kinetic theory proves that some of the most chaotic-looking systems in the universe can actually be understood and even predicted with just a few simple fundamental rules. It really makes you wonder, doesn't it? What other complex things in our world, maybe even things like traffic jams or stock market swings, are just waiting for us to find their own simple underlying rules?